this summary, and we started with Kirchhoff's law and proved that the emissive power and the absorptive power of every material, they have the same ratio. And if there is a body which has complete absorptivity, that is, if A is equal to 1, then its emissive power will be the universal function. It will not depend on what kind of body it is or what material it is. It is something which is a function of lambda, the wavelength, and the temperature at which it is radiating. So this can be simulated completely in a cavity, and that is also a black body radiation, and that is where most of the experiments were done. Now, it is possible to relate black body radiation with the energy density of radiation, and that is because energy is propagated at a finite speed. Therefore, in any volume, radiation coming from one side goes to the other side, and while it is traversing that region, it will leave its density there. So that is related to the specific intensity of light. This k nu or k lambda is simply the amount of energy in radiation which is crossing unit area in unit solid angle per unit time. You can take any small area dA, and the energy which is crossing perpendicular to it in unit solid angle is called k nu, and that is related to the energy density. This velocity of light comes precisely because of the reason I explained. Then Boltzmann proved that, including all wavelengths, if the energy density is taken, then that goes as fourth power of absolute temperature with which this radiation is being emitted or is in thermal equilibrium with. And this proof also we gave in first lecture, and this relationship is called Stephan-Boltzmann law, because Stephan looked at the temperatures of various bodies and the energy emitted by them, and on a very rough scale and experiments, he could guess that the energy which is emitted is proportional to fourth power of absolute temperature. So this pi times k, pi is the constant which comes if instead of just the normal radiation, but all directions on one side of the surface, if you integrate, this will become pi times k, and that goes as sigma t to the power 4. So this constant is called Stephan's constant. Its current value is 5.67 into 10 to the power minus 8 joules per second per meter square and per fourth power of degree Kelvin. And entropy of cavity radiation can also be written down, and that tells us that because of this formula of Boltzmann, where the energy density is proportional to T to the power 4, you can quickly calculate the entropy also, and that is just 4/3 times the entire energy divided by the absolute temperature. And in an adiabatic reversible process, you can say that T cube times V remains constant. You can multiply this U, which is proportional to T to the power 4, then you will and convert it into volume. So this is T cube V remains constant, and that is used in effectively in Wien's law, where you consider radiation inside a cavity, and with one of the reflecting walls being brought down or compressing the radiation inside, and doing it very slowly so that at every stage the radiation is in thermal equilibrium, then you find that because of the moving reflecting mirror, the wavelength or the frequency changes when it strikes the surface and then gets reflected because of the Doppler effect. And that is why energy gets transferred from one frequency to another, and if you keep a track of that, how much energy gets shifted, then you'll find that this quantity you knew, the energy density at temperature T and frequency range nu and d nu, that is equal to nu cube times a function of nu by T. That is, the frequency and the temperature, they go together. That is, if you increase the temperature, then the frequency also increases in that profile of this function. So we have this u, which is given by a function of nu by T multiplied by nu cube. And this is also something which is quite important, because if nu by T is taken as one function, then it goes to 0 when nu goes to 0, and at very large frequencies also it has to go to 0, unless the whole thing, otherwise the intensity will become infinity. So this function has a maximum, and that maximum will occur at some frequency or some wavelength, and there nu by T or the lambda into times T, that will be a constant, because it is a function of this ratio. So wherever that function has a maximum, that is not going to change. That particular value will then be a constant, and this lambda maximum into temperature, absolute temperature of black body radiation, is given by this number, which is 2898 10⁻⁻⁶. I had also given some examples of earliest measurements about 120 years before, in 1899 or something, which were done those experiments, and they had found some value which is very similar to this. And then we discussed what is the possible shape of this function, which is a function of nu by T, because this is going to be a universal thing which is immaterial. It does not depend on what kind of material which is emitting radiation. So Rayleigh-Jean's law, which is something which was which has a funny history, in the sense that it was totally unnoticed by Planck and all other scientists, whereas the experimentalists had seen it. And this was given precisely at a time at which Planck also gave his formula, I think a few months earlier. So Planck was unaware of it. But it is simply this, that this quantity F nu by T is actually this nu square by C cube, 8 pi nu square by C cube into KT. And this formula comes from classical mechanics. Whenever there is an oscillator, and in fact, this is something which is important about this subject, that since it does not matter what kind of matter is emitting radiation, you can also always assume that matter to be composed of a large number of oscillators of all possible frequencies, and then heat it up. So when these oscillators are oscillating, and if there is radiation falling on them, the electric field of that radiation will make these oscillators, which are charged dipoles, they will oscillate with greater amplitude. But when they oscillate, they also emit radiation because they are accelerated. As you know, every charged particle, when it is accelerated, it emits radiation. So that radiation is equal to the radiation which is energy which is given by the oscillating field, and the two come to a thermal equilibrium when the energy of the oscillator, average energy, becomes equal to the energy which is given by the radiation. And the relationship between the two is just this 8 pi nu square upon C cube. This comes from classical mechanics, from Maxwell's theory. It has nothing to do with any other new development. But this is KT is the average energy of an oscillator, because it has 2 degrees of freedom. Every oscillator has a kinetic part plus potential part, and that those 2 degrees of freedom contribute half KT each. So it is equal to this much. So Rayleigh-Jean's formula, which is a classical formula, will give us 8 pi nu cube by T multiplied by nu by T inverse. So that function is, in this case, is simply just this function, nu by T inverse. Whereas Vn also, at that time was looking at this formula, and he suggested that u nu should be alpha times e to the power minus nu by t into some constant. And his suggestion was based on some analogy with the Maxwell velocity distribution, where in Maxwell velocity distribution, as you know, it is some constant times exponential of minus the energy of each molecule divided by t. So in the kinetic theory of gases, if you take the analogy, then you write this, and it seems to go very well. It seems to very well explain the experimental results, because those experimental results at that time were being done in the visible region or something, for which this formula holds very well. The region for which Rayleigh-Jeans formula holds are long wavelengths. And long wavelengths, I suppose in 1900 or around that time, the technology was not good enough to measure microwaves or waves of longer wavelengths that accurately. These experiments were done at temperatures which were, I think, of the order of 1000 degrees centigrade, 1000 degrees Kelvin or something. And there, the nu which corresponds to them, or the maximum which corresponds to them, comes in that region. So there, this formula holds quite well, and these were quite successful. Now, Planck knew that this is only a formula suggested without any theory behind it. So he wanted to explain exactly this formula. And we discussed yesterday how he saw the two ends, and he was always looking at the entropy. He missed this Rayleigh-Jeans formula, which is based on classical mechanics, classical Maxwell field theory, and he somehow was interested in looking at the entropy. And that entropy wise, he found that the second derivative of entropy in one case goes as 1 upon u, and the other case it goes as 1 upon u squared. So by integrating, he found this formula, which is interpolating between the two. And this formula was exceedingly successful. Even the departures from Wien's formula could be explained by formula of this. And this also determined, I will probably explain what are the constants that he determined, Planck determined by his formula, because it was so well explained, the experimental numbers which were available at that time. He integrated, first of all, and obtained Stephen Boltzmann law. This is not surprising, because Stephen Boltzmann law will depend on that, but that establishes a relation between the Stephen Boltzmann constant and k to the power 4 upon h cube. And by calculating the maximum, he verified the displacement law, which corresponds to this lambda max into t, so that B is known. And from known values of sigma and B, he obtained H, that is 6.55, which is very close to current values, 10 to the power minus 27 a second, which today will be written as 10 to the power minus 34 joule second. And K, which is the Boltzmann constant, as 1.346 into 10 to the power minus 16 degree Kelvin. And the today's theory, probably today's value is 1.38, I think. So these are very close to these theories. And from known values of the gas constant, which is, you remember, the Boltzmann constant is the ratio of the gas constant R, which comes in PV is equal to RT, ideal gas equation, and divided by the Avogadro number. So R by N, once you know K and you know R, you can calculate N, which was 6.175 10 to the power 23 per mole, which is a very good number also. And from Faraday's constant, which is about how much charge is deposited in electrolysis per mole, that is, if N0 molecules of charge 1 or electrons of charge 1 are taken together, then the elementary unit of charge was obtained as 4.69 into 10 to the power minus 10 ESU. This is important because this was one of the first measurements, theoretical predictions of the charge of the electron coming from Avogadro number, which was coming from Planck's formula. So this gave a confirmation. In fact, people believed in Planck's theory also because it was giving a right value for the charge. Now, today we will begin with this background, Einstein's 1905 paper. It is called On a Heuristic Point of View Concerning the Production and Transformation of Light. It is in Analytical Physics and it's in German. This is the translation of the paper, and this English translation is available at this website, and this translation also appears in an American Journal of Physics paper by Arons and Pepper. So if you have access to American Journal of Physics, you can see it there. This is, of course, this is einsteinpapers.press.princeton.edu is there. Almost all Einstein's papers are available online and you can look at it there. And also I will very highly recommend this article by N. Mukunda, the story of the photon, which was published in Resonance in March 2000 and page 33. So this is something which I actually would recommend for you to read regarding the material which is in there in these 3 lectures, including today's lecture. In fact, there is more because which I cannot cover today, but Einstein's further work on the photon. So let's go through the Einstein's paper of 1905, and I also recommend you to read it because this is one of those papers for which I think your preparation is not so much needed. It is one of the clearest examples of well-written paper, which is so simple and even a student should be able to read it. And it, in any case, it gives you a flavor of the physics of those days. So let's go through. In fact, it has, I think, 8 sections, and I'm not numbering those sections, but we'll go through the whole of it, whatever he did. So the first thing that Einstein does is he kind of rediscovers Rayleigh-Jean's law. It is also well known that Einstein was not aware of Rayleigh-Jean's law. But of course, he was aware of this formula, which is Planck and also others. This is the classical formula I was talking about a little before, where the radiation density, the black body radiation density, is related to the oscillator's average energy when it is in thermal equilibrium with this radiation. So there is a factor of 8 pi by c cube into nu square, which comes from classical Maxwell theory. And this is the average energy. And what Einstein does is simply to substitute U oscillator as equal to KT, which is what would happen because there is a average energy per degree of freedom equal to half KT. This is something which Maxwell Boltzmann's kinetic theory of gases say. I am sure, and everybody is sure that Planck also knew about it. And if he had put this equal to U nu, he would have obtained Rayleigh-Jean's formula and probably would have given up his attempt to find the explanation for success of Wien's formula. Anyway, so if this is given, it is what I was saying, that Planck himself could have discovered this, but he did not do it, and it was lucky for us because he obtained the Planck's formula instead by combining that. Einstein then next shows that this formula will lead to infinity at high frequency. That is also no-brainer. Anybody can see this, that if you allow nu to go to high values, if you integrate it all, the whole energy will be infinity because there is nothing to dampen it. Unlike the Wien's formula, where there is an exponential of minus nu by kT. So this is also he shows in one section of the paper. And then he also remarks in a section that the value of the constants which like the Avogadro number, etc., which Planck determined, are actually independent of Planck's formula, but they can be in the Wien's classic limit or the classical limit. That is either Rayleigh-Jean's or Wien's law. You can always obtain it. please remember that Planck's formula has two constants, one in front of it. Let me show the formula. Here it is. Okay, there is an H here and there is a K here, or the the Boltzmann constant. So if you take the limit of if you take the limit when this is high, then of course H will be outside. But if you take the limit when this is if h nu by kt is small, then you will have h nu by kt in the denominator, and this h will cancel. So classical limit, to the classical limit, h is invisible. Okay, that's the point I want to make. The classical limit will see k, and this higher limit, or Wien's law, will see the other constants also through the exponential. You can plot a log versus that, and the slope will give you the value of k. So let me come back to what I was saying, that Einstein shows that this goes to infinity at high infinities, and then he remarks that the values of the constants can be determined without having any recourse to the Planck's formula as such. Then in the next section, Einstein rederives the equation delta S by delta U is 1 upon T. This is not really necessary, because Wien's and other thermodynamic relationships, it is well known that 1 upon T is delta S by delta U. The only point which is here is that this is small s and small u, they belong to particular frequencies. And the reason he gives is that in the radiation, when it is in thermal equilibrium, different frequencies, unless you are shifting their frequencies by reflectors and so on, which are moving reflectors, it will always have separate entropies. So the entropies of each frequency is separate, and the energy corresponding to that, energy density corresponding to that, will also be separate, and the two will have the same relationship as temperature. Another way to say it is this, that in a radiation, which is black body radiation, all different frequencies have the same common temperature. This is something which Planck also later on emphasized, that it is, you can think of only monochromatic radiation, which is in thermal equilibrium, but if you combine different frequencies with different temperatures, that will not be black body radiation. Black body radiation is characterized by the fact that all frequencies have the same common temperature. Next, Einstein takes the Wien's limit of Planck, and this is important, that he does not take the whole Planck formula, but takes the Wien limit of the Planck formula. And I am omitting this script nu from u, but please remember we are talking about some particular frequency. So the Wien's formula is equal to u alpha nu cubed e to the power minus h nu by kt. This is the Wien's formula. And so if I want to find out what 1 upon T is in this equation, I have to take the logarithm, and this log of u by alpha nu cube, you can bring it on this side. So u upon alpha nu cube log is equal to minus h nu over kt, or 1 upon T, just take this k and h on the other side, 1 upon T, which is ds by du, is equal to minus k upon h nu. From here, log of u divided by alpha nu cube. Okay, and this is integrable. You can you can easily integrate this with respect to u, so that you can get s as a function of u. This is simple, because integral of suppose I take x equal to u by alpha nu cube, then log of x or dx is just x log x minus 1. Okay, so you get s as a function of u, which is given by k upon h nu u times log of u upon alpha nu cube minus 1. This is very simple integral. And the entropy for volume V, if you multiply it by V as the volume, which has a total energy equal to U equal to small u times V. So remember that small u is energy density. So if you multiply it by volume, it will give you the energy contained in volume V. So the entropy for volume V is equal to minus K over H nu, and this small u becomes capital U, and inside if you substitute that capital U divided by volume as log of u small v alpha nu cube minus 1. This v u small v is multiplied on both sides, so you get S capital S here and capital U here, and inside this small u is converted into capital U. Okay, so this is the expression for entropy as a function of energy U and volume V. And if the same amount of energy is confined to a smaller to volume V and V0, the difference in entropies is this. Please remember that we are talking about the same amount of energy U. U is common, but volumes are different. So S minus S0 is minus K times U upon H nu, which is common to both, log of U upon V alpha nu cube minus log of U upon V0 alpha nu cube. And therefore, between these two, log of this minus log of this is log of the ratio, which is V upon V0, and K upon H nu will come outside. There is a minus sign which gets cancelled because log of small v is in the denominator. Log of 1 upon small v is minus of log of v. So you get log of V upon V0, which is equal to K times, and this, if you want, you can take this H nu in the power above. So U over H nu goes in the power above and only the K remains outside. So this is Einstein's formula for the difference in the entropy, which has the same amount of energy in the two different volumes. So it is in a way the volume dependence of entropy. Now, this is something which he compares with a simple formula which you all know. It is related to the Boltzmann formula, which tells us that entropy is K times log of W. Einstein expresses his differences from the Boltzmann formula. He says that in Boltzmann formula, W only refers to the all possible states or number of all possible states and combinatorics, whereas Einstein tries to justify this by saying that W refers to probabilities. And this is something important in the history of statistical mechanics also, because W being the number of possible states and W being the probability of those states, they are all closely related. But at that time, Einstein thought that his version of the formula is different and better. Anyway, that being so, he says that we get entropy or entropy differences as K times log of something. And what that log of something is, what he wants to understand and what he wants to explain. Now, let's look at the case of a large enclosure with a volume V in which small n molecules of a monatomic gas move around randomly and independently. So let's compare the formula that we have already obtained for entropy of radiation with the entropy of a number of point particles or molecules or atoms moving around in a large enclosure. So in this capital V volume, if there is a small volume small v inside, then for a single atom which moves randomly, the probability of its being found in a small v is small v divided by capital V. This is very simple because after all, when you want to have a molecule moving around totally randomly, the number of times it will be found or the possibility of its being found in small v will be dependent on what is its ratio with respect to the entire one. This is something, elementary probability. and the probability of all the n molecules, since they are all independent, they don't affect each other's probabilities. So that for n molecules will be V upon V, that is small v over capital V raised to the nth power. That is, it will be probability of the 2 will get multiplied, 3 will get multiplied. So if there are n number of molecules, the same probability will raise to power n. And now if there is another region of a, let us say, smaller volume V, then the probability for all of them to be in that region is small v0 upon V to the power n, just like this one. So what happens is that the probability of all the n molecules being together in a smaller volume is of course much smaller, and all of them being in a larger volume V is larger than that. So the entropy, the difference in entropy of the gas at temperature T confined in the two volumes is S minus S0 log of V upon V0 to the power n. The K times W to the power n minus K times W0 to the power n will simply give you this. This formula is well known, and let me also tell you, because it's a kind of something which we must feel, people don't usually write this kind of a formula. So Einstein's derivation is new, but then you look at this simple derivation which is there in thermodynamics, and everybody knows that, even students in high school would know that. Or if you have S minus S0, please remember that for perfect gas, the energy U of a perfect gas does not change because it only depends on temperature, and if you are keeping the same temperature, it will be isothermal expansion or compression. So S minus S0 will be 1 upon T from V0 to V to P times dV, and since P is K n times K times 1 upon V, you can always say P upon T equal to Nk over V. So it will be log of V dV over V, which is log of V upon V0 to the power n. Log of V minus log of V0. So it is K times, and this n can go to the power. So basically, this is the formula for n particles of a perfect gas or n molecules of a perfect gas and their entropy volume dependence. And now Einstein does the obvious thing of comparing these two formulas. That is, this is S minus S0 K times log of V minus V to the power n for a monatomic gas or perfect gas, and this is the formula for radiation. S minus S0 is K log of V minus V0 to the power U by h nu, which he derived from Wien's formula. What does it tell us? It tells us that this n, which is the number of molecules, is somehow of the same quantity as U over h nu, where U, you remember, is the total energy divided by h nu. So it looks like as if it is n, small n packets of energy which are giving us this. That this is the number of packets of energy which are moving around separately. Einstein's put it like this. It's a very bold idea. It says that monochromatic radiation, that is radiation of fixed frequency of low density, that is within the validity of the Wien's radiation formula, it behaves in thermodynamic respect as if it consists of mutually independent energy quanta of magnitude h nu. Because it is raised to the power n, it means that all those probabilities are independent. Now, this is one remark which I would like to make here, is that the total energy U in the two situations with volume V and V0 is the same. For the gas, the energy is also the same because it depends on the temperature and that remains the same. But in the case of compression or the radiation case, the same amount of energy is confined to a smaller volume, which means it will be a different energy density. And since nu is fixed, then it will be a different temperature. So the analogy should not be taken too far. analogy is about total amount of energy being the same and its volume dependence. Now, Einstein views the frequency of a quantum as something like its velocity, although all of them move with the velocity c. But then he compares the average kinetic energy of a molecule, which is 3 kT by 2 at thermal equilibrium at temperature T, which is half kT multiplied to 3, with the average energy of a quanta. This is, I think, in the next section of Einstein's paper. The all possible frequencies, assuming the Vn law to hold throughout, he integrates. Look at this. This is 0 to infinity alpha nu cube e to the power minus h nu over kT. This will be the total energy in all, including all frequencies. This is divided by 1 upon h nu times the energy, which means the number of particles which it has, and this is per particle how much energy is there, and that comes out to be 3 kT. So his way of saying it is that what you have as 3 times half kT, here it is 3 times 1 kT, which is, you know, the per energy quantum. That is the, but it is of course not kinetic energy averaged over as in the case of monatomic gas. In the next section, he then talks about the Stokes law in photoluminescence. Now he has got a picture in his mind in which radiation of frequency nu consists of packets of energy h nu, and then he says that Stokes law basically is this, that if radiation falls on photoluminescent matter, then it emits radiation, but the frequency of emitted radiation is always less than the absorbed frequency. And therefore, this Stokes law, he explains that there will be no lower limit to intensity to excite the fluorescent effect. This is very important because one can have a very strong intense light, or one can have very low light. But as long as there is energy which is enough to excite emitted energy, and that even one quantum, one photon will be able to do, that means that you don't have to, even if you go to very low intensities, even this packets of h nu will be able to excite. Whereas the classical wave theory will just say that there will be below a certain intensity, there will not be possible to excite photoluminescence. And this was experimentally verified, effectively saying that the number of quanta must be very small, but a single quantum can always kick out, or another can process another photon coming out of it. So, and he also makes remark about the photoionization of ultraviolet light. When ultraviolet light falls on it, there is ionization of gases, and so he makes a remark that that will also depend on this kind of phenomenon, that intensity will not matter for starting the phenomenon. And then, of course, he talks about which so much is being talked about. I will be very brief. This is emission of cathode rays through the illumination of solid bodies. That's the title of the section, which he, I think, discusses towards the last section. And there, the problem is cathode rays, of course, what he means are electrons. Basically, cathode rays, electrons were discovered in 1897 by Thomson, and that, I think, still people called those as cathode rays, the particles which were identified as electrons. So there's a very brief history of photoelectric effect. It will probably require another lecture for doing justice to that. Hertz had discovered in 1887 the photoelectric effect, and he was doing it experiments trying to show how electromagnetic waves travel from one place to another. Hertz, as you know, was the one person who demonstrated the existence of electromagnetic waves in laboratory, and that's his importance. And then he discovered that sometimes the spark produced, extra sparks, and the reason for that was that there were electrons, coming out in number because of those photo. So photoelectric effect, not fully this thing, was a side phenomenon which Hertz had noticed, and this Hallebachs also noticed that. And there are two high school teachers, Elster and Geitel, who also noted in 1890 this phenomenon. It was basically after the discovery of electron in 1897, then Thomson himself uh, determined this, and ultraviolet light causes the emission of electrons was a phenomenon noted by Thomson in an important paper. And then Philip Leonard in 1902, just 3 years before Einstein's paper, he could vary the light intensity by a factor of 1,000. And he noted that electron energy showed not the slightest dependence on light intensity. This is very important, because light intensity simply in classical wave theory would mean whether the electric vector and magnetic vector are large enough or not, and all energy is contained in that. Whereas if energy is contained in packets, it is only the frequency which determines how much energy is in each packet or each quantum. So this is something which actually was important. And in that paper, one of the last sections, actually the last section, contains this equation, which all of you must have seen it. It's called the photoelectric equation. It says that if h nu, if P is the energy which is needed for release of the electron from the surface of the metal, then the electron cannot have more than this the maximum energy it can have is h nu minus P. Of course, it can lose energy on the way, so the energy may be less than that, but it can never be more than this. And since this is a linear equation, it can determine the value of h. And this is what is even done in some MSc level experiments in our universities even today. So if P is the energy required for electron to escape from the metal surface, this can be subtracted, and that's the maximum energy. And Robert Millikan in 1916 measured the value of H to be 6.57 10 to the power minus 27. This is as early as 1916, and use of this equation. But that doesn't mean that the idea of the photon or the light quantum was accepted easily. There was great resistance to accept this idea of light quantum, and there are many reviews written on this, and I don't have the quote here, but Millikan in 1948, when he was approached by Abraham Pais on Einstein's 60th birthday, I think, then even in 1948, he was saying that I spent 10 years of my life trying to verify this equation and never found it deviating from its accuracy, but it is so unreasonable. And that's what he still believed in that. I mean, he couldn't just believe that it goes against the whole idea of interference of light. And that is something which people find so hard even today to accept, about how does interference can be explained by the photon concept. So I think I'll stop here and ask you to sort of go over it and ask the question. Please try to read Mukunda's article, which is really quite good, and it also gives you other ideas which I cannot explain here, about fluctuation and how Einstein related it to both the wave nature and the particle nature by considering fluctuations of energy density. So I'll stop here, please. Okay, and you can ask the questions which I will like to answer if I can answer.
So thank you so much, sir, for the very encouraging lecture. Now the session is open for discussion. Now the participants can unmute your mic and you can please ask any further questions you have. Or do you want to post the question in chat box? The participants are most welcome.
I'm keeping the screen because there may be some formulas people might ask questions about. Is that okay? I mean, I
Yes,
don't have
yes,
to show my face.
yes, fine.
Okay, this is well-known story, so probably.
If no questions, we can.
Yeah.
Yes, sir.
Close.
Yes. So if there are no more questions from participants, shall we wind up the session for today's session now? I mean, this session now.
This session can be.
Yes.
Okay.
And participants can join. Vijay sir, shall we join by 11:30 or till earlier, sir?
That's for Dr. Kapoor to answer.
Yes, 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 sir. Professor Kapoor, sir, or whether he's online sir, now?
Yeah, I'm here.
Yes, sir. By what time shall we start the session, sir?
Sorry? Yeah, we'll start at 11:30.
11:30. Okay. So participants.
If you want before that, because we have lost some time. It depends on you. You have to decide.
No, 11:30 will start the session, sir. Maybe till then, maybe the participants can leave the session now. Maybe we can start. We can have a demonstration with Dr. Ashok Kapoor, sir, whether the screen and everything is fine, and the participants can leave the session and they can join by 11:30. Will be okay, sir?
Yeah.
Okay.
Okay. Okay. Thanks.
Thank you so much, Dr. Pankaj Sharan, sir, professor from Jamia Millia Islamia, for the very kind lecture. So participants can please take a break and join the next session by 11:30 a.m. So the intimation will be sent through WhatsApp once again. Okay. Thank you so much. Dr. Ashok Kapoor, sir, we will have the mock demonstration session. Can you please unmute your mic and just share your screen, sir, so that if any technical issue is there, we can sort it out.
Yeah, I will check everything. If everything works fine, then it will be nice. So just give me some time to open the files I need. And
Good morning, Professor Kapoor, sir.
good morning. I am trying to open the files that I need.
Yes, sir. We'll check it, sir, now.
Then I will share the screen. So please wait.
Yes, sir. Amir, sir, stop recording, sir.
Yeah, you
Yes,
can
sir.
stop recording. Yes. No need to record.
Okay, sir.